A single galaxy contains more raw power than every weapon ever built. We are about to journey through the cosmos to rank the 30 most powerful forces in the universe. You will understand the hidden engines that twist space, shatter stars, and decide the ultimate fate of everything. What mysterious pressure is ripping the cosmos apart, and what invisible glue holds it all together. By the end, you will see reality not as a static picture, but as an epic battlefield of unimaginable energies. Which force do you think rules them all? It begins with a simple, everyday pull. Gravity is the universe's architect, the silent hand that sculpts worlds from cosmic dust and binds galaxies in a slow, stately dance. It is the force you feel when you drop a pen, the reason Earth circles the sun, and the invisible glue that holds the Milky Way together. For centuries, we understood it through Isaac Newton's law of universal gravitation, a brilliant idea that every object in the universe attracts every other with a force that weakens with distance. This single law explained the orbits of planets and the fall of an apple with elegant precision. But Albert Einstein gave us a far more radical vision. He proposed that gravity is not a force at all in the traditional sense. Instead, he saw it as the curvature of space-time itself. Picture a taut trampoline. Place a heavy bowling ball in the center and the fabric dips and warps. Now roll a marble nearby and it will spiral inward, not because of a mysterious pull, but because it is simply following the curved path created by the bowling ball's mass. That is Einstein's universe. Planets orbit stars because they are rolling along the curves in space-time that those massive stars create. Black holes, the ultimate expression of this idea, warp space-time so severely that not even light can climb out of the dip they create, leading to those iconic visualizations of light bending like a straw in a glass. On a human scale, gravity feels dominant, yet it is astonishingly weak compared to the other fundamental forces. The entire Earth's gravity pulls on you, yet you can overcome it with a simple jump. A tiny refrigerator magnet can defy that entire planetary pull and stick to your fridge, demonstrating that electromagnetism is vastly stronger at close range. But gravity has two supreme advantages. First, its range is infinite. Its influence, though fading, extends across the entire observable universe. Second, it only attracts, never repels. Over vast distances and immense scales, this relentless cumulative attraction allows it to dominate the cosmos. It gathers clouds of gas into stars, stars into galaxies, and galaxies into colossal clusters that stretch across billions of light years. So while it may be the weakest force in the laboratory, gravity is the master sculptor of the largest structures in existence, a gentle giant whose patience shapes the entire cosmic landscape. Yet for all its cosmic grandeur, gravity is utterly dwarfed in strength by the force that holds your very atoms together. This is electromagnetism, the fundamental power behind light itself, every chemical reaction, and the entire technological world humming around you. While gravity sculpts the universe on the grandest stage, electromagnetism writes the script for everything that happens on the smaller, more intimate stages of atoms and molecules. It governs the behavior of anything with an electric charge, from the protons in an atom's nucleus to the electrons whizzing around it. Think of it as having two inseparable faces, electric and magnetic, two sides of the same coin that can transform into one another. A moving electric charge creates a magnetic field, and a changing magnetic field can generate an electric current. This beautiful interplay is what allows generators to produce electricity and motors to spin. At its heart, electromagnetism is about attraction and repulsion. Opposite charges attract and like charges repel. This simple rule is the architect of matter. It is the glue that binds electrons to an atomic nucleus, preventing atoms from simply flying apart. It orchestrates the intricate dance of chemical bonds, determining how atoms link together to form every substance you see, touch, and are made of, from the water you drink to the DNA in your cells. You witness its raw power in a lightning bolt, where the buildup of electric charges in a storm cloud violently equalizes in a searing flash of energy. You feel its more gentle persuasion in a simple refrigerator magnet clinging to metal, a tiny demonstration of a force so potent that it can easily overpower the gravitational pull of an entire planet. Compared to gravity, electromagnetism is about 1,000 billion times stronger. That number is so astronomically large it defies everyday comprehension. It is the reason you do not fall through your chair. The atoms in the chair and the atoms in your body repel each other with electromagnetic force, a force so immensely powerful that it effortlessly counters the whole Earth's gravity pulling you down. Without it, solid matter would not exist. We would all collapse into formless clouds of particles. So while gravity builds the mountains, electromagnetism builds the rocks, the trees, and you. It is the force of structure, of light, of connection, and the invisible hand that literally shapes our reality at every single scale. But that incredible electromagnetic force has a fatal flaw for building the universe as we know it. It repels. Within the cramped confines of an atomic nucleus, positively charged protons are packed incredibly close together. The electromagnetic repulsion between them is monstrous, like trying to hold a dozen powerful magnets together with their same poles touching. According to electromagnetism alone, every atomic nucleus except the simplest hydrogen should instantly explode. Yet they do not. Something far more powerful is at work. A force so potent it makes electromagnetism look like a gentle breeze. This is the strong nuclear force, the universe's ultimate glue, and the single strongest fundamental force in all of existence. Its sole purpose is to bind the building blocks of matter together against impossible odds. It operates on two levels. First, it acts as the super glue for quarks, the fundamental particles that make up protons and neutrons. This aspect is called the color force, and it is so powerful that quarks are forever confined. You can never find a lone quark in nature. The force is that unbreakable. Second, a residual effect of this quark binding leaks out to bind protons and neutrons themselves together into atomic nuclei. This nuclear binding is what overcomes the fierce electromagnetic repulsion between protons. Imagine two powerful warriors locked in a constant, desperate struggle. On one side, electromagnetism is relentlessly pushing the protons apart. On the other, the strong nuclear force is pulling them together with a grip 100 times stronger. Within the tiny space of a nucleus, the strong force wins, but only just barely, and only over an incredibly short distance. Its range is minuscule, confined to a scale smaller than a single atom. Step just a femtometer away, about the width of a medium-sized nucleus, and its power vanishes almost completely. This is why atoms are mostly empty space, and why we do not feel this mighty force in our daily lives. But without it, there would be no stars, no planets, and no chemistry. The sun shines because the strong force allows hydrogen nuclei to fuse together into helium, releasing the energy that lights the cosmos. Every atom in your body, every element heavier than hydrogen, exists only because this mighty, short-range glue won a battle against electromagnetic fury at the dawn of time. But that mighty nuclear glue has a strange, shadowy counterpart. The weak nuclear force operates on an even more intimate scale, a ghostly hand that can reach inside a particle and change its very identity. It is the subtle architect of change, the force behind the quiet, relentless ticking of radioactive decay. While the strong force builds and binds, the weak force transforms. Its power lies not in strength, but in a unique ability to alter the fundamental flavor of particles themselves. The most famous example is what happens inside an unstable atomic nucleus. A neutron, left to its own devices, cannot survive forever. Through the weak force, one of the down quarks inside that neutron can spontaneously change into an up quark. In that instant, the neutron transforms into a proton. This metamorphosis releases an electron and an almost undetectable particle called a neutrino. This process, known as beta decay, is the weak force's signature move. It is the reason some elements are radioactive, slowly and steadily transforming into different elements over time. Without this strange, subtle force, the universe would be frozen. Neutrons would never turn into protons. The first and simplest element, hydrogen, which is just a single proton, could never have forged the building blocks for anything more complex. The weak force is the essential first step in the cosmic alchemy that builds the periodic table. Its role becomes spectacularly clear in the heart of our Sun. The Sun's power comes from fusing hydrogen into helium, but that process relies on the weak force to begin. Two protons, both positively charged, normally repel each other violently due to electromagnetism. To fuse, one of them must briefly become a neutron. That transformation is orchestrated by the weak force. It is a staggeringly slow process by atomic standards, which is why our Sun burns for billions of years rather than exploding in a flash. This delicate slowness, governed by the weak force, is what makes stable, life-nurturing stars possible. Later, in the cataclysmic infernos of supernovae, the weak force again plays a pivotal role. It helps govern the collapse of massive dying stars and the frantic synthesis of heavy elements like gold and uranium that are then scattered across the galaxy. So while it is feeble and short-ranged, the weak nuclear force is the universe's master of ceremonies for change. It is the quiet tick of a radioactive clock, the hidden step in stellar fire, and a crucial reason the cosmos is filled with the rich variety of elements that make planets, oceans, and life itself possible. Yet for all their power, the four fundamental forces are local actors on a cosmic stage that is being stretched apart by something far more profound. This is dark energy, the single most dominant component of our universe and its greatest modern mystery. It is not a force that pushes or pulls on matter in the traditional sense. Instead, dark energy appears to be a property of empty space itself, a kind of latent repulsive pressure that causes the very fabric of the cosmos to expand at an accelerating rate. For most of the 20th century, astronomers believed the universe's expansion, following the Big Bang, was gradually slowing down due to the relentless pull of gravity acting on all matter. The great question was whether that gravitational brake would one day reverse the expansion into a big crunch or merely slow it to a gentle coast. Then, in the late 1990s, two independent teams made a shocking discovery. By observing incredibly distant and ancient stellar explosions called Type 1, a supernova, which act as standard candles for measuring cosmic distances, they found that these far-off beacons were dimmer than expected. The inescapable conclusion was that the expansion of the universe is not slowing down at all. It is speeding up. Some unknown repulsive force, later dubbed dark energy, is overwhelming gravity's pull on the largest scales. Today's most precise measurements tell us dark energy constitutes about 68% of the total energy content of the cosmos. All the stars, galaxies, planets, gas, dust, and even the invisible dark matter we will discuss later, everything we consider the universe's stuff, makes up less than a third of what is actually out there. The dominant force shaping the cosmic future is the energy of seemingly empty space. Its nature remains one of physics' deepest puzzles. The leading idea is that it is a cosmological constant, a fixed energy density inherent to the vacuum of space. As the universe expands and more space comes into existence, more of this repulsive energy appears, driving the expansion ever faster. The ultimate implications are staggering. If dark energy continues unchanging, it points to a cold, lonely fate for the cosmos. Galaxies beyond our local group will eventually be pushed away so fast their light can never reach us, leaving our sky dark and empty. Distant civilizations of the far future would see only their own galaxy, with no evidence of a broader universe or its explosive beginning. Dark energy is not just another force on the list, it is the force currently writing the final chapter of everything. But if dark energy is the mysterious pressure pushing the cosmos apart, another unseen hand is desperately holding it together. This is dark matter, the invisible skeleton upon which the entire visible universe is built. We cannot see it, touch it, or detect it with any telescope that observes light, yet we know it is there because of its immense gravitational pull. It is the ghost in the cosmic machine, and without it, our galaxies would simply fly apart. The first compelling evidence came from the way galaxies spin. In the 1930s, astronomer Fritz Zwicky studied the Coma cluster of galaxies and found their motions were far too fast for the gravity of their visible stars to hold them together. He proposed the existence of Dunkel Materie, or dark matter, to provide the missing mass. Decades later, Vera Rubin provided irrefutable proof by meticulously mapping the rotation of individual spiral galaxies. She expected stars at the outer edges of a galaxy, far from the bright central bulge, to orbit more slowly, just as Pluto orbits our Sun much slower than Earth. Instead, she found stars at the very outskirts whizzing around just as fast as those near the center. The only explanation was that each galaxy is embedded in a vast spherical halo of invisible matter, extending far beyond its luminous stars. This dark matter halo provides the extra gravitational glue to keep those high-speed outer stars from being flung into the void. We see its fingerprints everywhere. When we look at massive galaxy clusters, we often see distorted, stretched, and duplicated images of galaxies behind them. This phenomenon, called gravitational lensing, occurs because the cluster's immense gravity, mostly from dark matter, warps the fabric of space-time like a giant lens, bending the path of light from more distant objects. By measuring this distortion, we can literally map the distribution of the unseen dark matter. On the grandest scale, dark matter acted as the cosmic scaffolding for all structure. After the Big Bang, ordinary matter was a hot, smooth soup of particles, too energetic to clump together easily. Dark matter, being unaffected by light or radiation, could begin collapsing under its own gravity much earlier. It formed vast, web-like filaments and dense halos, creating gravitational wells that then pulled in the normal gas. Stars and galaxies formed along these invisible dark matter highways, painting luminous cities upon a dark framework. So what is it made of? The leading candidate is a theorized particle called a WIMP, a weakly interacting massive particle. As the name suggests, it would have mass, making it gravitationally significant, but it would interact with normal matter only through gravity and the weak nuclear force, making it incredibly difficult to detect. Countless experiments deep underground, shielded from cosmic rays, are searching for the rare, telltale bump of a WIMP colliding with an atomic nucleus. Other possibilities include sterile neutrinos or even primordial black holes, but the mystery endures. One thing is certain: dark matter outweighs normal matter by a factor of about 5 to 1. For every galaxy you see shining in the night sky, there is 5 times more unseen mass holding it in place, weaving the cosmic web that defines the architecture of our universe. The quiet work of dark matter may build the cosmic scaffolding, but it is a far more violent and brilliant force that fills that structure with the raw materials for everything we know. A supernova is not merely a star dying. It is the universe's ultimate forge, a cataclysmic detonation that for a few fleeting weeks can outshine the combined light of every star in its host galaxy. This is the moment gravity, after patiently holding a star together for millions or billions of years, suddenly turns traitor and unleashes hell. There are 2 primary paths to this stellar apocalypse, each a masterpiece of cosmic violence. The first, a core collapse supernova, is the fate of massive stars at least 8 times heavier than our Sun. For its entire life, such a star is a titanic battleground. In its core, the relentless crush of gravity is balanced by the outward pressure of nuclear fusion, as it progressively burns hydrogen into helium, helium into carbon, and so on, forging heavier elements layer by layer like a cosmic onion. This balancing act continues until the core finally creates iron. Iron is nuclear ash. Fusing iron does not release energy, it consumes it. In that instant, the star's central engine shuts off. With no outward pressure to counter it, gravity wins absolutely. The core, now an iron ball the size of Earth but containing more mass than our Sun, collapses at nearly a quarter the speed of light. In less than a second, protons and electrons are crushed together into neutrons, and the core becomes an unimaginably dense neutron star. The outer layers of the star, suddenly with nothing underneath them, come crashing down in a furious rush, only to rebound off this newly formed, ultra-hard neutron surface. This rebound creates a shock wave of incomprehensible power that blasts outward, tearing the entire star apart in a fireball of pure energy. The second type, a thermonuclear supernova, is even more titanic. It occurs in binary star systems where a dense stellar corpse called a white dwarf siphons material from a companion star. As the white dwarf's mass creeps toward a critical limit, about 1.4 times the mass of our Sun, the pressure and temperature in its core become so extreme that a runaway nuclear fusion reaction ignites almost instantly. The entire white dwarf, a carbon and oxygen sphere, undergoes a total thermonuclear detonation. There is no remnant core, no neutron star left behind. The star is completely vaporized in an explosion so uniform and so bright it can be used as a standard candle to measure the depths of the universe. In both cases, the energy released is almost beyond comprehension. For a brief moment, the supernova can emit more energy than our Sun will over its entire 10 billion-year lifetime. But its true power is not just in light, it is in creation. The ferocious heat and pressure within the expanding blast wave are the only places in the universe violent enough to forge the heaviest elements. The gold in a wedding ring, the uranium in a power plant, the iodine in your body, all were cooked in these stellar explosions. The shockwave then acts as a cosmic gardener, hurling these newly forged elements across light years, enriching vast clouds of gas and dust. This stellar debris becomes the nursery for the next generation of stars, planets, and ultimately, life. We are literally made of star stuff, the scattered ashes of these ancient, magnificent cataclysms. Every breath you take contains atoms forged in a supernova that exploded billions of years before our Sun was born. That stellar forge creates the very elements of planets, but it also leaves behind the universe's most perfect trap. A black hole is not an object in the traditional sense. It is a region of space where gravity has won the final, absolute victory. The boundary of this region is called the event horizon, the point of no return. Within this invisible sphere, the gravitational pull is so unimaginably strong that the escape velocity exceeds the speed of light. Since nothing in the universe can travel faster than light, nothing, not a single particle, not a flicker of radiation, can ever break free. It is a one-way door from which there is no exit, a tear in the cosmic fabric where the normal rules of physics cease to apply. The force at the event horizon is so extreme it warps time itself. To a distant observer, a clock falling toward a black hole would appear to tick slower and slower, freezing entirely at the horizon. For the unfortunate object crossing that threshold, however, the journey continues toward the central singularity, a point of infinite density where our current understanding of physics completely breaks down. The approach to a black hole is a terrifying spectacle of tidal forces. An astronaut falling feet first toward a stellar mass black hole would experience a difference in gravity so severe between their head and their toes that they would be stretched into a long, thin strand of atoms, a process grimly nicknamed spaghettification. Long before reaching the event horizon, matter is shredded into its fundamental particles. Yet black holes are not just cosmic vacuums. they are often surrounded by brilliant, chaotic halos of light and energy. As gas, dust, and even entire stars are drawn inward, they do not fall straight in. Instead, they spiral into a flat, superheated disk called an accretion disk, orbiting at nearly the speed of light. The friction and magnetic forces within this disk heat the material to millions of degrees, causing it to blaze with X-rays and gamma rays, making these invisible monsters some of the brightest objects in the high-energy sky. At the centers of most galaxies, including our own Milky Way, lurk monsters of a different scale, supermassive black holes weighing millions or even billions of times the mass of our Sun. These are not the products of a single star's death, but giants that grew over cosmic time, feasting on gas and merging with other black holes. Their gravitational influence is so vast it governs the orbits of stars in the galactic core and may play a crucial role in shaping the entire galaxy's formation. In April 2019, the Event Horizon Telescope collaboration gave us our first direct image of one, the supermassive black hole at the heart of galaxy M87. That now iconic orange ring of light is not the event horizon itself, but the silhouette of the black hole against the glowing backdrop of its own accretion disk, a shadow of ultimate gravity cast upon the fire of doomed matter. This single image confirmed a century-old prediction and made the most extreme gravitational force in the universe a tangible, observable reality. But even the awesome fury of a supernova can be dwarfed by something far more focused and lethal. Gamma-ray bursts are the single most powerful explosions in the universe since its fiery birth. Not broad fireballs but cosmic blowtorches, concentrating incomprehensible energy into beams of light so intense they can briefly outshine every star in the observable cosmos combined. These are not random flashes, they are the death cries of the most extreme stellar objects, and they come in two distinct, terrifying varieties. The longer bursts, lasting from 2 seconds to several minutes, are thought to be the final act of a special kind of supernova. When a truly colossal star, dozens of times more massive than our Sun, collapses at the end of its life, it does not simply explode outward. Instead, the collapsing core may form a black hole so rapidly that it funnels the star's dying energy into two narrow, opposing jets that scream outward at nearly the speed of light. If one of those jets is pointed directly at Earth, we see it as a long gamma-ray burst, a blinding spike of the highest energy radiation. The shorter bursts, lasting less than 2 seconds, have an even more violent origin. They are believed to be the final milliseconds of a cataclysmic dance between two ultra-dense stellar corpses, neutron stars. As these city-sized balls of pure neutronium spiral together over millennia, they finally merge in a collision of unbelievable density. The resulting fireball, likely forming a black hole almost instantly, also launches those same ultra-relativistic jets, creating a short, impossibly bright flash of gamma rays. The numbers defy belief. In the span of a few seconds, a single gamma-ray burst can release more energy than our Sun will emit across its entire 10 billion-year lifespan. All that power is not spread in a sphere, but focused into those narrow beams, making them the most luminous electromagnetic events known. For a planet unlucky enough to lie in the crosshairs of such a beam, even from thousands of light-years away, the consequences could be apocalyptic. The initial blast of gamma rays would strip the planet's upper atmosphere, destroying the ozone layer that protects life from the Sun's ultraviolet radiation. The aftermath could trigger chemical reactions creating nitrogen oxide smog, blocking sunlight and potentially plunging the world into a prolonged, deadly ice age. Scientists suspect a gamma-ray burst may have contributed to the Ordovician mass extinction on Earth some 450 million years ago. These events are rare in any given galaxy, but in a universe filled with hundreds of billions of them, they serve as a stark reminder of the violent forces that constantly reshape the cosmos, capable of ending epochs of life with a flash of light from across the galaxy. These focused beams of death are terrifying, but they are mere firecrackers compared to the engines that can illuminate an entire cosmic epoch. Quasars are the universe's ultimate lighthouses, powered by the most ravenous supermassive black holes imaginable. At the heart of a distant galaxy, a black hole weighing billions of suns is not dormant, it is feasting. A colossal whirlpool of gas, known as an accretion disk, spirals inward at relativistic speeds, heated to millions of degrees by friction and glowing with the light of 1 trillion stars. But the true spectacle is not the disk itself, nor even the black hole's insatiable hunger. It is what the black hole cannot swallow. Not all the doomed material makes it past the event horizon. Through processes we are still unraveling, involving intense magnetic fields wound up by the disk's furious rotation, a fraction of the superheated plasma is channeled away from the poles and launched into space at nearly the speed of light. These are quasar jets, twin beams of matter and energy so powerful they can stretch for hundreds of thousands of light years, far beyond the boundaries of their host galaxy. They are not simple streams of gas. They are particle accelerators on a cosmic scale. Within these jets, electrons and protons are whipped to velocities so extreme that when they encounter magnetic fields, they emit a brilliant synchrotron radiation across the entire electromagnetic spectrum, from radio waves to lethal gamma rays. The result is a beacon so luminous it can outshine every single star in its galaxy by a factor of 1,000. For a sense of scale, a single quasar can be as bright as 1 trillion suns, visible to us across more than 10 billion light-years of expanding space. They serve as crucial landmarks in the early universe, their light acting as a backlight to illuminate the faint, gossamer threads of the cosmic web. Yet their power is not just in light but in raw kinetic force. These jets carry enough energy to reshape entire galaxies, heating and blowing away the gas that would form new stars, effectively putting a cosmic brake on galactic growth. They are the universe's most dramatic feedback mechanism, where a monster at a galaxy's core dictates its future from within. But the universe's grandest structures, from quasars to galaxy clusters, all trace their origin back to a moment of impossible growth. Cosmic inflation is the theory that in the first sliver of a second after the Big Bang, the universe underwent a burst of expansion so violent it defies all intuition. For a fleeting interval, perhaps as short as 10 to the power of -36 seconds, the cosmos did not just expand, it inflated, doubling in size over and over again at a rate far faster than the speed of light. This was not an expansion of matter into space, but a stretching of space itself, a runaway repulsion woven into the fabric of reality. The driving force behind this epoch is thought to be a hypothetical energy field called the inflaton field. Picture a ball resting at the top of a very flat, very high hill. This position represents a state of false vacuum with a tremendous energy density. As this ball, representing the inflaton field's value, begins to slowly roll down the hill, its energy drives the exponential expansion of space. When the ball finally reaches the bottom and settles, that energy is released as a hot fireball of particles and radiation, what we traditionally call the Big Bang. This single idea solves profound mysteries. The first is the horizon problem. Look at the cosmic microwave background, the afterglow of the Big Bang. Its temperature is almost perfectly uniform in every direction we look. Yet, according to standard cosmology without inflation, these distant regions of the early universe were too far apart to have ever been in thermal contact, to have exchanged heat and reached the same temperature. It is like walking into a room and finding 2 cups of coffee on opposite sides, both at exactly 70 degrees Celsius, without any connection between them. Inflation solves this by proposing that these vastly separated regions were once intimately connected, packed into a volume smaller than a proton before inflation stretched them apart. They had time to even out their temperature before the great stretching began. The second mystery is the flatness problem. our universe's geometry, as best we can measure, is astonishingly flat, like a perfectly stretched sheet. For it to remain so flat over 14 billion years of expansion, its initial conditions had to be fine-tuned to an unimaginable precision. Inflation acts like a cosmic magnifying glass, taking any tiny, curved region of the early universe and stretching it so enormously that it appears flat to us, just as the surface of a balloon appears flatter as you blow it up. But perhaps its most crucial gift was imperfection. Quantum fluctuations, tiny jitters inherent to all fields, were happening during inflation. As space expanded exponentially, these microscopic ripples in the inflattened field were stretched to astronomical sizes. These became the seeds of all future structure. Slightly denser regions where the inflattened field had a tiny bit more energy would eventually, under gravity's pull, become the galaxies and clusters we see today. The slightly less dense regions became the vast cosmic voids. In this way, the grand tapestry of the cosmos, with its glittering galaxies and dark, empty spaces, was woven from quantum noise magnified by the most powerful expansive force the universe has ever known. Those quantum seeds of structure grew into galaxies, and within them, stars lived and died. The most extreme of these stellar corpses do not fade quietly. They become cosmic magnets of almost inconceivable power. A magnetar is a neutron star that has crossed into a realm of such intense ferocity it defies belief. It is born from the same core collapse supernova that creates a typical neutron star, but under special conditions that amplify its magnetic field to levels that border on the absurd. To grasp this scale, consider Earth's magnetic field, the gentle force that guides a compass needle. A hospital MRI machine uses a field about 30,000 times stronger. A neutron star's typical field is already 1,000,000,000,000 times stronger than Earth's, but a magnetar, its magnetic field is another 1,000 times stronger still, reaching 1,000,000,000,000 times the strength of the field protecting our planet. This is not merely a number, it is a fundamental reshaping of reality in the space around the star. If a magnetar were located as far away as the Moon, its magnetic field would effortlessly erase the data from every credit card on Earth. Venture closer and the field becomes a lethal force of physics itself. Matter cannot exist in a normal state here. Atoms are stretched into long, thin cylinders, their electron clouds distorted beyond recognition. The field is so powerful it influences the very vacuum of space, affecting the behavior of virtual particles that flicker in and out of existence. This unimaginable stress has a terrifying physical consequence. The magnetar's crust, a crystalline shell of iron nuclei 10 billion times stronger than steel, is under constant, unbearable strain. Eventually, it cracks. This is a starquake. Imagine an earthquake, but on a sphere 20 kilometers across with a crust harder than diamond, snapping under magnetic pressure greater than the gravitational binding force holding the star together. When the crust fractures, it releases pent-up energy in a cataclysmic instant. The entire star rings like a bell, and its magnetic field lines whip and reconnect, accelerating particles to near light speed. The result is a sudden, blinding flash of X-rays and gamma rays so intense that for a fraction of a second, a magnetar can outshine every other source of high-energy light in our entire Milky Way galaxy. We have witnessed these events. In December 2004, a magnetar 50,000 light-years away in the constellation Sagittarius unleashed a burst that, for a fifth of a second, outshone the full moon. It saturated every X-ray and gamma-ray detector in Earth's orbit, ionized our upper atmosphere, and briefly changed the shape of our planet's magnetic field. It was the most powerful transient event ever recorded from outside our solar system. Magnetars represent the ultimate expression of magnetic force in the cosmos, a demonstration that the universe can concentrate familiar physics into a realm of such extremity that it becomes a new form of violence. Yet that extreme magnetic power is anchored to something with mass, a property we take for granted but whose origin is one of physics' deepest secrets. Why does anything have mass at all? The answer lies not in a force that pushes or pulls, but in an invisible cosmic molasses that fills every corner of the universe. This is the Higgs field, an energy field that permeates all of space, and its interaction with particles is what grants them the property we call mass. Without it, the universe would be a featureless, chaotic blur. The idea is beautifully counterintuitive. In the vacuum of empty space, according to quantum field theory, there is no true emptiness. Instead, it seethes with invisible fields. The electromagnetic field is one, and its ripples are what we call photons or light. The Higgs field is another, but unlike the electromagnetic field, it has a non-zero value everywhere. Think of it like a vast, invisible ocean. Different particles move through this ocean in different ways. Some particles, like photons, the particles of light, do not interact with the Higgs field at all. They sail through this cosmic molasses completely unimpeded, which is why they have no mass and travel at the ultimate speed limit, the speed of light. Other particles do interact. Quarks and electrons, the building blocks of atoms, feel a kind of drag as they move through the Higgs field. This resistance to acceleration is what we experience as mass. The stronger the interaction, the more mass the particle has. A top quark interacts very strongly, making it incredibly heavy. An electron interacts only weakly, giving it a tiny mass. This mechanism, proposed in the 1960s by Peter Higgs and others, was the final missing piece of the standard model of particle physics. For decades, it was a brilliant but unproven idea. The smoking gun would be to find a ripple in the Higgs field itself, a particle that would prove the field existed. That particle is the Higgs boson. Finding it required recreating the conditions of the universe a trillionth of a second after the Big Bang. This was the monumental task of the Large Hadron Collider, a 27-kilometer ring buried beneath the French-Swiss border. Inside its superconducting tunnels, protons are accelerated to 99.9999991% the speed of light and smashed together head-on. These collisions concentrate immense energy into a tiny point, momentarily shaking the fabric of space-time and exciting the Higgs field, causing it to ripple and produce a Higgs boson. The boson itself is incredibly unstable, decaying into other particles in a fraction of a nanosecond. On July 4, 2012, after analyzing quadrillions of such collisions, scientists at CERN announced they had found it. They had captured the fingerprint of the Higgs boson in their detectors, confirming the existence of the field that gives mass to the universe. This discovery was monumental. It validated a half-century of theoretical work and completed our picture of the fundamental particles, but its true power is in what it means for the cosmos. Mass is not an intrinsic property handed down from nowhere. It is an acquired trait, a conversation between a particle and an all-pervasive field. Without this conversation, without mass, particles would zip around at light speed. Gravity, which acts on mass, would have nothing to grasp. Atoms could never form, stars could never ignite, and the structured, complex universe of galaxies, planets, and life would be impossible. The Higgs field is the silent, cosmic sculptor that turned a formless, energetic soup into a universe of substance. It is the reason there is something rather than nothing that has weight, that can clump together, and that can ultimately build everything we see and are. Mass is the anchor, but gravity's true power is revealed in its differences. Tidal forces are not about the strength of gravity's pull, but the terrifying variation in that pull across an object. This is the gradient, the cosmic stretching machine that can heat worlds, raise oceans, and shred matter into streams of atoms. The classic example is our own moon's effect on Earth. The side of our planet facing the moon feels a slightly stronger gravitational tug than the side facing away. This difference, this stretching force, pulls the oceans into two subtle bulges, one toward the moon and one away. As Earth rotates beneath these bulges, we experience the rhythmic rise and fall of the tides, a gentle but constant reminder of this differential force. For a far more dramatic display, look to Jupiter's volcanic moon, Io. Io orbits so close to the massive gas giant that Jupiter's gravity exerts a monstrous pull. But the true stress comes from Io's slightly elliptical orbit and the gravitational tugs of Jupiter's other large moons, Europa and Ganymede. These influences cause Io to flex and bend as it travels, with Jupiter's gravity pulling harder on the side of Io facing it and less on the far side. This constant, needing tidal flexing generates immense internal friction, heating Io's interior to a molten frenzy. The result is a world that looks like a cosmic pizza, dotted with hundreds of active volcanoes that constantly resurface it, making Io the most volcanically active body in our entire solar system. Its surface is a hellscape of sulfurous plains and towering eruption plumes, all powered not by internal radioactive decay alone, but by the relentless gravitational massage of a giant planet. This same principle reaches its ultimate, terrifying extreme near a black hole, a scenario we call spaghettification. Imagine an astronaut falling feet first toward a stellar mass black hole. Their feet, being closer to the black hole's center, feel a vastly stronger gravitational pull than their head. This difference is not a gentle tug. It is an overwhelming force that stretches their body into a long, thin strand of atoms like pulling on a piece of taffy. Long before reaching the event horizon, any object, be it a star, a planet, or a spacecraft, is torn apart into a stream of elementary particles by this extreme tidal gradient. It is a stark demonstration that in the universe it is often not the average force that matters, but the difference from one point to another. From the gentle lapping of waves on a shore to the volcanic infernos of distant moons and the absolute disintegration at the edge of reality, tidal forces show us that gravity's most dramatic effects come from its subtle, and sometimes not so subtle, imbalances. The magnetic fury of a magnetar is an exotic spectacle, but our own star provides a more intimate and constant reminder of such power. Solar flares and coronal mass ejections are the sun's explosive tantrums, moments when our seemingly steady star unleashes the pent-up energy of its own twisted magnetic fields. These events begin in the sun's atmosphere, the corona, where magnetic field lines arc and loop, anchoring themselves in the turbulent plasma of the solar surface. Like overstretched rubber bands, these lines can become twisted and stressed over time, storing immense amounts of energy. When the tension becomes too great, the field lines suddenly snap and reconnect in a new, lower-energy configuration. This magnetic reconnection happens in an instant, but the release is catastrophic. It acts like a cosmic slingshot, accelerating charged particles to nearly the speed of light and heating the surrounding plasma to tens of millions of degrees. The initial flash is a solar flare, a burst of radiation across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. This light reaches Earth in just over 8 minutes, a silent but potent barrage. Often, the reconnection event is so violent it does more than just flash. It can blow a colossal bubble of the sun's own atmosphere right off into space. This is a coronal mass ejection, a billion-ton cloud of magnetized plasma hurled outward at millions of kilometers per hour. Think of it not as a flame, but as a hurricane of charged particles and magnetic fields, a storm front traveling through the solar system. When these storms are directed at Earth, the consequences are both beautiful and dangerous. The charged particles follow the lines of our planet's magnetic field, funneling toward the poles where they collide with atoms in the upper atmosphere. This collision energizes those atoms, causing them to glow in ethereal curtains of green, red, and purple, the aurora borealis and aurora australis, but the beauty masks a significant threat. The incoming blast of particles induces powerful electric currents in the ground and in our long-distance power lines. In March 1989, a coronal mass ejection caused a massive geomagnetic storm that collapsed the entire Hydro-Quebec power grid in Canada in under 2 minutes, leaving millions in the dark for 9 hours. Satellites are even more vulnerable, their delicate electronics fried by the radiation, and astronauts outside Earth's protective magnetic bubble face serious health risks from the particle bombardment. These solar storms are a humbling demonstration that the force which nurtures life on our planet is also a dynamic, occasionally violent entity. They remind us that we orbit a star that is very much alive, capable of reaching across 150 million kilometers of empty space to flick the lights off in our cities with a single magnetic sneeze. Our sun's magnetic tantrums are local fireworks compared to the slow-motion apocalypse unfolding on a galactic scale. 2 spiral galaxies, each containing hundreds of billions of stars, are on an inescapable collision course, drawn together by the patient, relentless pull of gravity across the void. This is not a sudden crash, but a billion-year dance of destruction and creation, a force of cosmic restructuring so immense it rewrites the architecture of the heavens. Our own Milky Way is living this story, locked in a gravitational embrace with the Andromeda Galaxy. Right now, they are rushing toward each other at about 110 kilometers per second. In roughly 4 billion years, they will begin their first close pass, a gravitational encounter that will stretch and distort their beautiful spiral arms into long, streaming tails of stars. The popular image of a galactic collision is one of stellar cataclysm, with suns smashing into each other in brilliant explosions. Yet, in this vast and mostly empty space, that is the one thing that almost never happens. The average distance between stars in a galaxy is so enormous that a direct stellar collision is extraordinarily rare. The real action and the true force of the event happens to the immense clouds of gas and dust that drift between those stars. As the galaxies intermingle, these colossal clouds, each light years across, slam into one another. The collision compresses the gas, triggering violent shockwaves that ripple through the clouds. In these compressed, turbulent regions, the force of gravity finds its moment. Dense knots of gas collapse under their own weight, igniting the birth of millions of new stars all at once. We see this in other merging galaxies across the universe, their cores glowing with the fierce blue light of newborn massive stars, a phenomenon called a starburst. This wave of stellar creation can be so intense it exhausts a galaxy's gas reserves in a relative blink of an eye. Meanwhile, the invisible halos of dark matter that surround each galaxy, containing most of their mass, also interact. They pass through one another, but their gravitational pull acts like a cosmic brake, slowing the visible stars and gas, ensuring the galaxies do not simply fly apart after their first encounter. They will swing around, fall back together, and merge again and again over hundreds of millions of years. With each pass, their structures are torn apart. The elegant spiral disks are utterly destroyed, their stars thrown into chaotic orbits. Eventually, the two systems will coalesce into a single, new galaxy, most likely a featureless elliptical blob, its star-forming gas either used up in the starburst or blown away by the ferocious radiation from all those new stars. This is gravity's patient masterpiece, a force that works over timescales we can scarcely comprehend. It demonstrates that the universe's most powerful restructuring often comes not from a sudden blast, but from a slow, inevitable embrace that transforms two majestic spirals into something entirely new, a monument to the enduring power of attraction written across billions of years. That galactic collision rewrites structure on the grandest scale, but beneath it all, the very definition of emptiness is a lie. According to quantum mechanics, there is no such thing as a true vacuum, a place of perfect nothingness. Even in the deepest, darkest void between galaxies, space itself is alive with a faint, fizzing energy. This is the quantum vacuum, a seething sea of transient particles and fields that pop into and out of existence in a relentless, ghostly dance. These are quantum fluctuations, Borrowing energy from the universe for an unimaginably brief moment, particle-antiparticle pairs spontaneously appear, only to annihilate each other and vanish a fraction of a nanosecond later. This is not a theoretical fantasy, it is a verified prediction of quantum field theory with real, observable consequences. One of the most striking proofs is the Casimir effect. Take two uncharged, perfectly smooth metal plates and place them incredibly close together in a vacuum, just a few millionths of a meter apart. In the gap between the plates, only certain wavelengths of these virtual particles can flicker into being. Outside the plates, all wavelengths are possible. This creates a subtle pressure difference, with more virtual particles pushing on the outside of the plates than on the inside. The result, the two plates are gently pulled together by the force of nothingness itself. Scientists have measured this tiny but real force, a direct fingerprint of the quantum vacuum's restless energy. This background hum of creation and destruction is called zero-point energy, the lowest possible energy a quantum system can have, and it is never zero. It is a fundamental, inescapable feature of reality woven into the fabric of space-time. This leads to one of the greatest puzzles in modern cosmology. When physicists try to calculate how much energy this quantum vacuum should contribute to the universe, the number they get is absurd. It is off by a factor of 1 followed by 120 zeros compared to the amount of dark energy we actually observe accelerating the cosmos. This colossal mismatch, the worst prediction in the history of science, is known as the cosmological constant problem. It suggests that either our understanding of the quantum vacuum is profoundly incomplete, or that dark energy is something else entirely, perhaps a dynamic field that has changed over time. Yet the possibility remains that this faint fizz of virtual particles, scaled up to the entirety of the universe, is the engine of cosmic acceleration. If so, vacuum energy would be the most ubiquitous force of all, a silent, omnipresent pressure inherent to every cubic centimeter of space, from the void between stars to the air in your lungs. It is a power so subtle we cannot feel it, so fundamental we cannot switch it off, and so immense in potential that it may literally be deciding the ultimate fate of everything. That faint fizz of the quantum vacuum is the background hum of reality, but in our own galactic neighborhood, we can witness its most spectacular consequences on a smaller, more intimate stage. Scattered throughout the Milky Way are stellar mass black holes and neutron stars locked in a deadly gravitational dance with a normal star. These binary systems are not quiet. They become microquasars, scaled-down versions of the brilliant monsters at the hearts of distant galaxies, and they offer us a front-row seat to the violent physics of relativistic jets. The process is a familiar, terrifying loop. The black hole or neutron star, an object with the mass of several suns compressed into a sphere just kilometers wide, exerts a ferocious gravitational pull on its companion star. It strips gas from the star's outer layers, drawing that material into a swirling, superheated accretion disk. Friction within this disk heats the gas to millions of degrees, causing it to glow brightly in X-rays. But the true spectacle begins when some of that infalling matter, instead of crossing the event horizon, gets caught in powerful magnetic fields generated by the spinning of the central object. Like a cosmic railgun, these fields channel and accelerate a fraction of the plasma into two narrow, opposing beams that scream away at nearly the speed of light. These are relativistic jets, and in a microquasar, they may stretch only a few light-years instead of the hundreds of thousands seen from a true quasar. Yet the physics is identical. The jets are so focused and energetic that we can detect their radio emissions from across the galaxy. One of the most famous examples is a system called SS-433, located about 18,000 light-years away. It consists of a black hole or neutron star orbiting a massive hot star. Its jets are not steady, they flicker and change direction over time, providing a dynamic laboratory. By studying the flickering X-rays from the accretion disk and correlating them with changes in the radio jets, astronomers can trace how the inflow of matter directly fuels the outflow of these incredible beams. Microquasars teach us that the ability to launch relativistic jets is not a privilege reserved for supermassive giants. It is a fundamental consequence of extreme gravity, intense magnetism, and rapid spin, a universal engine that can operate on any scale where the conditions are right. Watching these stellar systems flare and jet in our own galaxy is like having a detailed scale model of the universe's most powerful particle accelerators, allowing us to decode the precise mechanics that turn a black hole's feast into a focused beam of raw cosmic power. Light itself can push. It sounds impossible, for a photon is a massless packet of pure energy, yet it carries momentum, a gentle but insistent nudge it can impart to anything it strikes. This is radiation pressure, the physical force of light, and its subtle touch is written across the cosmos. You can see its most beautiful effect in the delicate sweep of a comet's tail. As a comet approaches the sun, its icy nucleus heats up, releasing gas and dust. The sunlight falling on these tiny particles does two things. Its energy heats them, but its momentum also pushes them. The finer dust particles are literally shoved backward by the sunlight's pressure, forming the comet's broad, curved dust tail that gently arcs behind it. Meanwhile, the sun's ultraviolet radiation ionizes the gas, which is then swept away by the solar wind, forming a separate, straighter ion tail that always points directly away from the sun. Two tails sculpted by two different aspects of the sun's radiant force. This gentle pressure also sets a fundamental limit on nature's grandeur. There is a ceiling to how massive a star can become, and radiation pressure is the architect of that ceiling. In the core of a truly massive star, the nuclear fusion reactions rage with such ferocity that they produce an unimaginable flood of photons. These photons, fighting their way out through the star's immense layers, exert an outward pressure that rivals the inward crush of gravity. For stars above about 150 solar masses, this radiation pressure becomes so powerful it begins to overcome gravity's grip. The star becomes unstable, pulsating violently and shedding its outer layers in tremendous eruptions. It cannot hold itself together. The light it creates literally starts to blow it apart, preventing the universe from forging stable stars of unlimited size. But this same force that limits stars could one day carry us to them. The concept of a light sail turns this gentle push into a propulsion system. A large, ultra-thin, reflective sheet deployed in space could catch the momentum of photons from the sun or from powerful Earth-based lasers. Each photon's push is minuscule, but they are countless and relentless. Without needing any fuel, a light sail could accelerate a small probe to a significant fraction of light speed over time, enabling missions to other stars within a human lifetime. Projects like Breakthrough Starshot envision using gigawatt-powered laser arrays to push gram-scale nanocraft to Proxima Centauri in just 20 years. It is the quietest engine imaginable, a sail pushed by starlight, harnessing the most ubiquitous force in the universe to voyage between the stars, from sculpting celestial visitors to constraining stellar giants and offering a pathway to other suns. Radiation pressure proves that even the gentlest touch, when applied across cosmic scales and time, can shape destinies. Every force we have witnessed, from the gentlest quantum flicker to the mightiest galactic collision, traces its lineage back to a single foundational moment. The Big Bang is not an explosion that happened somewhere in space. It is the explosive origin of space and time themselves. Around 13.8 billion years ago, the entire observable universe was compressed into a state of near-infinite density and temperature, a singularity where our current laws of physics simply break down. Then it began to expand. This was not an expansion into a pre-existing void, but the rapid stretching of the very fabric of reality, creating more space between every point as time began to tick forward. From that initial furnace of pure energy, everything we know was forged. In the first fractions of a second during the epoch of cosmic inflation, space itself ballooned at a rate faster than light, smoothing and flattening the cosmos. As it expanded and cooled, the fundamental forces froze out one by one from a unified superforce. Gravity separated first, then the strong nuclear force, and finally the weak and electromagnetic forces went their separate ways, setting the stage for all future physics. Within minutes, the universe had cooled enough for protons and neutrons to form and fuse into the first light elements, hydrogen and helium, in a process called Big Bang nucleosynthesis. For hundreds of thousands of years, the cosmos remained a hot, opaque fog of plasma, light trapped in a constant dance with charged particles. Then, as it cooled further, electrons combined with nuclei to form neutral atoms. The universe suddenly became transparent, and that first light, now stretched by 14 billion years of expansion, still washes over us today as the cosmic microwave background, a faint whisper of the birth of everything. Every galaxy, every star, every planet, and every law that governs them was set in motion by that single, unimaginably powerful event. It was the ultimate release of potential, the moment when all the forces we have ranked were born and the entire story of the cosmos began. That faint afterglow from the cosmic birth is still visible today, a ghostly light that fills every direction in the sky. The cosmic microwave background radiation is the oldest light we can see, a snapshot of the universe as it was just 380,000 years after the Big Bang. Before that moment, the cosmos was a searing, opaque plasma, a hot soup of protons, electrons, and photons constantly scattering off each other. As expansion cooled the universe, it finally reached a temperature where electrons could combine with nuclei to form stable, neutral atoms. In that instant, the fog cleared. Photons, the particles of light which had been trapped in the chaotic dance, were suddenly set free to travel across the cosmos. That first flash of transparency has been traveling for over 13 billion years, stretched by the expansion of space itself from visible light into the microwave part of the spectrum. It is a uniform, cold glow, now just 2.7 degrees above absolute zero, and it is everywhere. Finding it was one of the greatest discoveries of the 20th century. In the 1960s, Arno Penzias and Robert Wilson at Bell Labs were troubleshooting a persistent, annoying hiss in a sensitive radio antenna. It was the same in every direction, day and night, and they could not eliminate it. After ruling out pigeon droppings and other earthly interference, they realized they were hearing the echo of creation itself, the cooled remnant of the universe's fiery beginning. This cosmic microwave background is the ultimate baby picture of the cosmos, but this picture is not perfectly smooth. When we look with exquisitely sensitive instruments like the Planck satellite, we see it is painted with incredibly subtle variations, tiny patches that are just millionths of a degree warmer or cooler than the average. These are not flaws, they are the fingerprints of the infant universe's structure, the seeds of everything to come. Those minute temperature fluctuations correspond directly to slight differences in density. Slightly denser regions, where the universe was a tiny bit more crowded, appear as slightly cooler spots in the microwave background, a subtle effect of gravitational redshift. These over-dense patches had a gravitational head start. Over the eons that followed, gravity acted like a cosmic amplifier, relentlessly pulling more and more matter toward those dense seeds. The slightly warmer, under-dense regions, meanwhile, evolved into the vast cosmic voids we see today. Every galaxy, every cluster, every filament in the cosmic web can trace its lineage back to a specific pattern of hot and cold in that ancient light. By studying the precise statistics of these speckles, cosmologists can read the universe's vital signs, its age, composition, geometry, and even the details of the inflationary burst that planted the seeds. This afterglow is more than a relic, it is a direct message from the universe's first moments, a map that shows how the single, unimaginable force of the Big Bang imprinted a pattern of potential that gravity would spend billions of years sculpting into the galaxies and the voids that define our cosmic home. That cosmic afterglow captures the universe in its infancy, a moment when its laws were already distinct. Yet physics whispers of an even earlier time, a fleeting instant when the cosmos was so unimaginably hot and dense that the very forces we now see as separate were fused into one. This is the dream of a theory of everything, a single, elegant framework that could describe all of reality, from the dance of subatomic particles to the whirl of galaxies. It is a quest to uncover the universe's original, unified language. The journey begins with a profound realization. The strength of a force is not constant. It depends on the energy of the particles involved. At the low energies of our everyday world, the four fundamental forces appear wildly different. Gravity is incredibly weak, the strong force is locked inside nuclei, and electromagnetism and the weak force seem unrelated. But as we dial up the energy, simulating conditions closer to the Big Bang, something remarkable happens. The forces begin to change, their relative strengths start to converge. In the 1970s, physicists successfully showed that at energies around 100 billion times that of the Large Hadron Collider, the electromagnetic force and the weak nuclear force merge into a single electroweak force. This was a monumental unification, proving that two seemingly distinct forces are actually different facets of a more fundamental interaction. The next step is a grand unified theory, or GUT. This ambitious idea proposes that at even higher energies, the electroweak force and the strong nuclear force also become one. In this scorching realm, quarks and leptons, the building blocks of matter, would be interchangeable. A quark could transform into an electron, and protons, the stable heart of atoms, would no longer be stable. They could decay. This prediction leads to experiments deep underground, monitoring huge tanks of ultra-pure water, searching for the telltale flash of a single proton decaying. So far, none have been seen, suggesting the unification energy is even higher than we thought. But the ultimate challenge remains gravity. Incorporating Einstein's general relativity, which describes the cosmos on its largest scales, with quantum mechanics, which governs the smallest, has proven to be physics' greatest puzzle. At the tiny Planck scale, where quantum fluctuations should make spacetime foam and boil, our mathematics breaks down completely. This is where string theory and its successor, M-theory, enter the stage. They propose that the fundamental constituents of reality are not point-like particles, but unimaginably small, vibrating strings or membranes. The different notes of vibration correspond to different particles and forces. In this view, gravity, electromagnetism, and the nuclear forces all arise from the same underlying symphony of strings. It paints a breathtaking picture of the universe's first moments. For a sliver of time after the Big Bang, all matter and energy were compressed into a state of such extreme energy that a single, sublime superforce governed everything. There was no distinction between the force that holds atoms together and the force that bends the path of light. Reality was simpler, more symmetric, and unimaginably powerful. Then, as the newborn universe expanded and cooled, this perfect symmetry broke like water freezing into ice crystals. The one superforce crystallized out into the distinct forces we recognize today, each taking on its own role in shaping the cosmos. Finding the mathematical key to that primordial unity would be more than a scientific triumph. It would be a glimpse into the mind of the universe, revealing a fundamental elegance hidden beneath the complexity we see now. The search for a single cosmic language inevitably leads us to the edge of the known, to forces that are pure speculation but born from profound necessity. These are the theoretical titans, ideas crafted by physicists to explain the gaps in our understanding, to give shape to the universe's deepest mysteries. One such idea is quintessence. Unlike the static cosmological constant, Quintessence proposes that dark energy is a dynamic field, slowly evolving over cosmic time. Imagine it not as a fixed property of space, but as a kind of cosmic breath, a fifth element that can either strengthen or fade. This could explain why the acceleration of the universe appears to have changed over its history, offering a more nuanced story than a simple constant repulsion. Then there are cosmic strings, hypothetical one-dimensional scars in the fabric of space-time, theorized to have formed during the universe's early phase transitions. As the fundamental forces split apart, these defects would be unimaginably thin but under immense tension. A single cosmic string, thinner than a proton but stretching across the cosmos, could have the mass of a mountain range packed into every mile. Their gravitational influence would be bizarre, acting like a lens that creates double images of distant galaxies. If one were to pass through Earth, it would not cut the planet in half, but the strange geometry of space around it would cause a sudden, measurable shift in the distances between objects, a silent, invisible slice through reality itself. Perhaps the most mind-bending speculation comes from string theory, which suggests our universe may have more than the three spatial dimensions we experience. These extra dimensions could be curled up or compactified at scales a billion times smaller than an atom. The force of gravity in this view might appear weak to us not because it is inherently feeble, but because it is leaking into these hidden dimensions, its strength diluted across realities we cannot perceive. In such a cosmos, what we perceive as the fundamental forces might merely be shadows cast by vibrations in a higher dimensional realm. While none of these forces have been observed, they are not idle fantasy. They are the direct result of mathematicians and physicists following the equations to their logical, often startling conclusions. They represent the human drive to push past the horizon of current knowledge, to invent new concepts powerful enough to possibly explain the behavior of everything. These speculative forces remind us that our list of the universe's most powerful entities is not closed. It is a living document waiting for the next great discovery to rewrite it entirely. From the invisible glue inside an atom to the shadowy pressure tearing the cosmos apart, the universe is a hierarchy of unimaginable power. We have journeyed from the subatomic dominion of the strong nuclear force, which binds reality itself against electromagnetic rebellion, to the cosmic scale dominance of dark energy, an anti-gravity currently writing the final, lonely chapter of everything. In between lies a spectrum of titans, each ruling its own domain. Magnetars warp the vacuum with magnetic fury, supernovae forge the elements of life in stellar infernos, and black holes carve prisons of pure gravity from which nothing escapes. These are not isolated phenomena, they are a symphony. The weak force's subtle alchemy allows stars to burn steadily. The Higgs field gives particles the mass that gravity can grasp. Galactic collisions driven by that same gravity recycle gas into new generations of stars. This intricate, often violent interplay is not chaos, it is a precise, if brutal, recipe. Without the specific strengths and roles of each force, from the strongest to the most mysterious, our universe would be a formless, dark, and lifeless void. There would be no planets to orbit, no stars to shine, no chemistry to build complexity, and no observers to wonder at it all. Our existence is a fragile gift, balanced on a knife edge of cosmic forces that could obliterate us in an instant, yet have conspired over billions of years to create a stable niche where life can arise and ask these very questions. So as we look up at the night sky, we are not just seeing points of light. We are witnessing the ongoing battlefield and the grand collaboration of the 30 most powerful entities in existence. Which of these forces left you most in awe? Was it the patient universe-sculpting hand of gravity, or the instantaneous, star-shattering power of a gamma-ray burst? Share your thoughts in the comments below, and if you want to continue exploring the deepest mysteries of space, make sure to subscribe for more journeys to the edge of understanding.